inversion and constant TAS, what will happen? So let's say this is your Earth surface. Now what is an inversion? Inversion is an atmospheric phenomenon where you encounter increase in temperature with increase in height. Again, increase in temperature with increase in height. Normally, ISA conditions, what we expect, atmospheric temperature should decrease as you climb to higher altitudes. Inversion is the opposite of that. As you go to higher altitudes, atmospheric pressure increases. So, let's say there will be warm temperature first, and after some time you will encounter cold temperatures. Okay, you will have normal cool temperatures as you go to higher altitudes. So this phenomenon is called inversion layer, where you encounter warmer temperatures as you go to higher and higher altitudes. So now you are descending through such a layer in inversion layer. So like this. So what will happen? Okay, so what will happen? You are descending at constant true airspeed. At constant true airspeed. Now first things first, let's address calibrated airspeed. Now calibrated airspeed is nothing but a representation of dynamic pressure. Now dynamic pressure, what happens to atmospheric pressure when you descend to lower altitudes? Atmospheric pressure increases. Pressure increases. If atmospheric pressure increases, the atmospheric pressure that will be registered by your airspeed indicator, nothing but a pressure instrument, will also increase. More pressure will be available for its working, for its registration, processing, right? So if atmospheric pressure increases, that means the dynamic pressure that this airspeed indicator will measure or calculate or register will also increase. If dynamic pressure increases in the same amount or in the same proportion, the calibrated airspeed will also increase. That's why when you are flying at constant true airspeed, so true airspeed you don't change, but since you are climbing, descending to lower altitudes, atmospheric pressure increases, and this increase in atmospheric pressure is matched by increase in calibrated airspeed indication. So this delta option, calibrated airspeed decreases, is wrong. This will happen when you climb to higher altitudes at constant true airspeed. At high altitudes, you get lower and lower atmospheric pressures. This lower pressures will translate into lower dynamic pressure and hence lower calibrated airspeed indication. Now we are left with Mach number. Now let's say you are descending from an altitude where temperature was 15 degrees Celsius to an altitude where the temperature is more than 15 degrees Celsius. It's warmer than that. So let's consider you're descending to an altitude where now temperature is uh, 30 degrees Celsius. Okay. So what will happen? So for example, let's take this 15 and let's say you're descending from a temperature where there is 30 degrees Celsius to a temperature where the temperature or to an altitude where temperature is colder than that. So 30 ka will take 15. Okay, so you're descending from a warm layer into a cold layer. Okay, so over here also there will be cool layer, and then in midway you have warm layer. So that is inversion. That is, you go to higher altitudes, you have colder temperature, but you're expecting warmer temperature. So this is an inverse or opposite of what is normally found. Now, what will be the local speed of sound? Local speed of sound at 30 degrees Celsius. It will be equal to 39.17 square root of temperature in Kelvin. So 30 plus 273 is 303. So square root of 303 is 17.4 multiplied by 39.17, 682 knots. So Mach number will be TAS divided by local speed of sound. What is TAS? Let's say constant TAS is 300. You're descending at 300 knots, very fast. Local speed of sound 682. So Mach number is 300 divided by 682, 0.439 or 0.44. Now when you come to lower altitudes, suddenly you are getting cold temperatures. So 30 Celsius has become 15 Celsius. So now here local speed of sound will be 15 degrees Celsius. That means 39.17 square root of 273 plus 15, 288. Square root of 288 multiplied by 39.17 is 665, approximately 665. So TAS divided by local speed of sound equals to your Mach number. So TAS 300, local speed of sound 665. So 300 divided by 665 is 0.45. 0.45. So what has happened here? Mach number has increased from 0.44 to a new value of 0.45. Right? So that means when you descend through an inversion layer at constant true airspeed, Mach number increases. Option A. Mach number increases. You can see here, local speed of sound here was 682 in warm temperatures. Cold temperatures, it has reduced or decreased to a new value of 665. That means, and true airspeed is 300. So in situation 1, your true airspeed, I will write it here, your true airspeed was 300 knots and local speed of sound is 682. So the difference between them is this much, 682 minus 300, 682 minus 300, that is 382 knots. Now when you descend to cooler altitudes, the true airspeed is again the same. We have considered it as 300, local speed of sound 665. So what has happened? The difference between them, the space margin between them has become 365. So 382 has become 365 now. So the spacing or the difference between them has decreased. That means true airspeed has moved closer to local speed of sound here. So as you move closer and closer to the local speed of sound, Mach number will increase, because what is Mach number? It is nothing but true airspeed as a fraction of local speed of sound. Okay. So correct option is option alpha. Next, when you are climbing through an inversion at constant TAS. Now this was descending through an inversion at constant true airspeed. Now this is the opposite of that. You are climbing through an inversion at constant TAS. So what will happen when you are climbing? What will happen? First, you will encounter 15 degrees Celsius, and since it's an inversion layer, all of a sudden you will encounter warm temperature. So reverse will happen. So 0.45 will become 0.44. Okay. So Mach number will decrease. Mach number will decrease. The concept remains the same. Next, question number 33. When descending through an inversion at constant calibrated airspeed. Okay, so it's an inversion layer. You're descending at constant calibrated airspeed. What will happen to true airspeed, Mach number, and this? So now remember, you're descending through an inversion layer. So let's say this is your Earth surface. As you go to higher altitudes, this is the Earth surface. Here there are cool temperatures, and since it's an inversion layer, all of a sudden as you climb to higher altitudes, you encounter warmer temperatures. You must encounter cooler and cooler temperatures, but here Since it's an inversion layer, you encounter warm temperatures. Now you're descending in such a layer at constant calibrated airspeed. At constant calibrated airspeed. Now when you descend to lower altitudes, what happens? Atmospheric pressure, atmospheric pressure increases. Correct? Atmospheric pressure increases. Now your airspeed indicator is nothing but a pressure instrument. It's a pressure instrument. This pressure instrument will register atmospheric pressure, mainly the dynamic pressure. And this dynamic pressure will be shown to us in the form of a calibrated airspeed or indicated airspeed. So what will happen when you descend to lower altitudes? When you descend to lower altitudes, atmospheric pressure increases irrespective of temperature of the air, right? Now, if you are descending at constant calibrated airspeed, what will happen to true airspeed? Now, let's say you're descending at a constant true airspeed of your aircraft. So, what will happen to calibrated airspeed? Automatically, calibrated airspeed indication will start increasing in value. Why will it start increasing in value? Because now it's going to receive or register more and more atmospheric pressure, because atmospheric pressure increases as you come closer to the earth. Okay, so more and more pressure, more and more dynamic pressure, that will translate into more and more calibrated airspeed indication or indicated airspeed indication. Okay, so this is what should happen if you are descending at a particular true airspeed of your aircraft. But if you are calibrated airspeed will increase. Now you are deliberately maintaining the calibrated airspeed of your aircraft in your descent, meaning you are preventing your aircraft or the calibrated airspeed of your aircraft from increasing. You are stopping that from happening. Now to stop that from happening, what will you have to do? Okay, now normally calibrated airspeed should increase. But if you want to decrease that calibrated airspeed, you want to maintain that calibrated airspeed as you come down from higher altitudes, you will have to, you will have to, have to decrease, decrease the true airspeed of your aircraft. You will have to decrease the true airspeed of your aircraft. The calibrated airspeed is expected to increase because more pressure is available. Now, in order to prevent that from happening, what will you have to do? You will have to take away some of the pressure. Now, you cannot take away or eliminate atmospheric pressure, but what you can do is you can decrease the true airspeed of your aircraft. When you decrease the forward speed of your aircraft, automatically dynamic pressure, that is the pressure created by the relative airflow, will decrease. When that decreases, the speed shown by your speed indicator will also decrease by same proportion. So in order to maintain a constant calibrated airspeed, you will have to keep decreasing the true airspeed of your aircraft, so less and less dynamic pressure is available. Okay, so increase in static pressure as you come down to lower altitudes is compensated by decrease in dynamic pressure. So that is how a balance is struck between increase in pressure and decrease in dynamic pressure if you want to maintain a constant calibrated airspeed throughout your descent. So the correct answer here is true airspeed decreases. Calibrated airspeed doesn't depend on atmospheric temperature. So whether you are descending in an inversion layer, isothermal layer, a normal ISA temperature, ISA atmosphere, that doesn't matter. Calibrated airspeed is not dependent on any one of them, on any of them. So true airspeed should decrease. 34. When climbing through an inversion at constant calibrated airspeed. Okay, so now you are doing the opposite. Here you were descending, here you are climbing. So if you want to climb at constant calibrated airspeed, your true airspeed should increase. Why? When you climb to higher altitudes, atmospheric pressure decreases. Atmospheric pressure decreases, that means dynamic pressure decrease. So calibrated airspeed will also decrease. Now, if you want to prevent that from happening, if you want to prevent that calibrated airspeed from decreasing in value, you will have to give it some additional pressure. Okay, you will have to compensate for the decreasing static pressure around you. So how will you provide for that additional pressure? You will increase the forward speed of your aircraft. That means the true airspeed of your aircraft. When you do that, the dynamic pressure created by the forward speed of your aircraft, the additional dynamic pressure will compensate for that lower static pressure surrounding you, and hence calibrated airspeed will be prevented from decreasing or falling. So true airspeed should increase. 35. When climbing through an inversion at constant Mach number. Okay, now you're climbing at constant Mach number. What will happen? So you're climbing. So like I said before, when you are climbing to higher altitudes, irrespective of inversion layer, isothermal layer, a normal ISA atmospheric layer, your calibrated airspeed must decrease because calibrated airspeed is dependent on dynamic pressure. When you go to higher altitudes, pressure decreases. So pressure registered by airspeed indicator will also decrease, and that much decrease in calibrated airspeed will be noted. So you're climbing. So what should happen to your calibrated airspeed? It should uh, decrease. Okay, so it cannot increase. Now you are left with three values, three options: task, increase, decrease, remain constant. So let's take this your, let's consider this is your earth layer. Consider the earth. This is the cool atmospheric layer close to the earth's surface where temperature is 15 degrees Celsius. Now since it's an inversion layer, you are going to suddenly encounter warmer temperatures at high altitudes. That's not normal, but still in inversion that is the norm. So you're climbing at constant Mach number. Consider your Mach number is 0.8. Now the local speed of sound at 15 degrees Celsius will be 39.17 square root of temperature in Kelvin. So 15 plus 273 equals to 288 Kelvin. Square root of 288 into 39.17 is 665. At 30 degrees Celsius, the local speed of sound will be 39.17 square root of 273 plus 30, that is 303. Square root of that into 39.17 is 682 knots. So local speed of sound in cool temperatures is 665. In warm temperatures, it increases to a new value of 682. Now Mach number at both places is the same because you are climbing at constant Mach number. Now let's check what happens to the true airspeed. True airspeed here will be Mach number multiplied by local speed of sound. So 0.8 multiplied by 665. So 665 multiplied by zero point 0.8 is 532. Over here the task will be Mach multiplied by local speed of sound. So 0.8 multiplied by 682 is equal to 546 knots. So what has happened to true airspeed? It has increased from 532 to a new value of 546. Okay, so the answer will be task increases. Next, when you are descending through an inversion at constant Mach number, what will happen? Task will decrease. Task will decrease. Okay, so it's the opposite of this. You are climbing through an inversion at constant Mach number. Task increases. Okay, and here you are descending through an inversion at constant Mach number. So task will decrease. Okay, task will decrease. Now when you are descending to lower altitudes, atmospheric pressure increases. If atmospheric pressure increases, the registration of pressure by airspeed indicator will also increase, right? So accordingly dynamic pressure will be increased, and so calibrated airspeed must also increase. So here you have another option, delta, calibrated airspeed increase. So maybe it's a printing error or something like that, but it's safe to select Bravo, task decreases, because I have shown you the proof here, and calibrated airspeed also increases. So this should not be an option. If this is an option, this should be the option. So just be careful. Next. When climbing through an inversion at constant Mach number. So you are climbing through an inversion at constant Mach number. Your true airspeed is expected to increase. CAS decreases, yes, because when you are climbing, you always get lower atmospheric pressure. So this part is also right. When you are climbing through an inversion, local speed of sound will increase. 665 has become 682. So this is wrong. CAS remains constant, no, wrong. So again, possibilities, both possibilities alpha and delta are the right ones. It's better to select delta. Next. When descending through an inversion at constant Mach number, again CAS will increase. Okay, atmospheric pressure increases, so CAS increases. Local speed of sound should decrease, cannot remain constant. Local speed of sound will remain constant in an isothermal layer. The temperature is constant. CAS decreases. So yes. So delta is the right one. Next. When descending through an inversion at constant CAS. So it's similar to the previous question. If you are descending at constant calibrated airspeed, so you are decreasing the true airspeed of your aircraft. You are eliminating some of the dynamic pressure, so that increase in static pressure is compensated or balanced by decrease in dynamic pressure. So Bravo is the right answer. Okay, if you don't do that, calibrated airspeed will go on increasing as you go down to lower and lower altitudes, since the atmospheric pressure increases there. Okay, so if you want to prevent that from happening, if you want to stop the calibrated airspeed from increasing steadily, you want to maintain it, so decrease the forward speed of your aircraft. That will decrease dynamic pressure, and hence uh, it will decrease calibrated airspeed or indicated airspeed indication. So Bravo is the right one. So this concludes the lecture. I hope you have understood all the 10 questions that I have solved answering this video lecture. Now these 10 questions were theoretical. It didn't involve any mathematical equation or mathematical understanding apart from the fact that we used local speed of sound formula and Mach number formula. Most of it was theoretical, basic understanding of ISA atmosphere, ISA conditions, okay, understanding of inversion, isothermal layer, basic concepts of calibrated airspeed, true airspeed, Mach number, local speed of sound. When you know this basic details of these key topics, you will be able to find the answer to such questions by applying this knowledge, okay, the way I did, drawing the diagram, putting these basics into picture, and then deriving the information. Okay, so it's a bit difficult, it's not difficult, but it's tricky to memorize all the possibilities: inversion, isothermal, ISA, increase in climbing at constant walk, climbing at constant task, climbing at constant through airspeed. So it's a bit tricky to remember all the possibilities, all the combinations. So it's better to draw a picture so you get a clear understanding, you know what's happening. So that is how I do this particular question. So I hope you have understood my method, and if you are comfortable in that, you can inculcate this habit in your studies, and you can follow this method in your exam as well. Many questions like this won't be asked in your exam, maybe one, two, but not many. So it's not a very big issue. So with this, I'll stop here. All the best, and we'll meet in the next video lecture in which we are expected to solve similar questions. So I'll see you there.